Hello community! Today we're gonna do some real professional AI reasoning. You know, the hardcore stuff. So today we have a look at A star, at Q learning, and at Q star reasoning. So this complete research here addresses now the issue of errors, hallucination, and inconsistencies that LLMs encounter during now a complex multi-step reasoning process, which is based on their architecture, which is of course an autoregressive generation process. And I showed you in my last video 5 beautiful, simple reasoning steps, but now we are in the Profi League, so let's start. Now, of course, we formalize here a multi-step reasoning process of LLMs as a Markov decision process. And if we have a Markov decision process, you know we need now a state of the system, as denotes here the concatenation of an input question and a partial reasoning trace. We have here an action A. A denotes here the next reasoning step generated by the LLM, and we have a deterministic state transition T. Of course, we work here with reward function to measure how well the question is solved, plus the LLM has to develop here a policy that is parameterized by the factors theta, policy embodied by an LLM. And if we have all of those ingredients, we have the Markov decision process and we have an LLM policy P theta, now we are in the position here to calculate the value of a state action pair. And this value, this quality value, is given by a Q function. And the Q function now, if we do an optimization of an optimal policy P star, is called now the optimal Q function Q star. And Q star, you know, this satisfies here the Bellman optimality equation. And this is it. You just have to calculate this here for each and every LLM included here in the code. And you have here a beautiful decision-making multi-step reasoning LLM process defined as a Markov decision process. That's all there is to it. Now you might say, hey, wait a second, can I have a different view? Can you explain this maybe in a little bit more different way? Of course. So, AI models, like our large language model or vision language model, they have various algorithms and tricks to solve complex problems, to optimize the decision-making efficiency, and they more or less all fail. So what we know about it currently, we're talking about Q learning, A star, and Q star. Now, Q learning is an old fellow of us. We know this for a long time. This is fundamental in reinforcement learning of our LLMs, helping our AI agents to learn here the optimal action sets. A star, also an old friend of us, is crucial in path finding and in the graph traversal, ensuring that the shortest path on our graph structure is found efficiently. And the new kid on the block is now Q star. Now, Q star has one goal: to enhance the multi-step reasoning in our LLMs and VLMs, using now the principle from both the Q learning and the A star methodology. And in this short video guide, I will cover here this algorithm in detail, highlight the mechanism, the application, and I will compare them. So, easy. What is the mechanism of Q learning? You know this. We have an AI agent that explores the environment, let's say a robot moving in a room, and this robot takes action and receives rewards for the action taken. The Q value is now updated using here our classical Bellman equation. And this iterative process continues until the Q values, the quality values, converge. This means simply that our AI agent has learned the optimal policy for moving around in this new environment. And by balancing now the exploration phase and the exploitation phase, so what we will discover newly and what we already know, what is our homemade knowledge, in this balance, in this delicate balance here, the agent improves its performance over time. Now, it is known that the classical mechanism of A star is here. You have two sets of lists. You have an open list containing the start node and a closed list to track here the explored nodes. And for each node in your graph, you calculate here the cost, and it has a heuristic function. And combining them both to form here the evaluation function f of n. And the algorithm selects now the node with the lowest function f value, expands it by adding its neighbors to the open list and updates their cost. And you repeat this process until you found the shortest path. And now the mechanism of Q star as I told you, a framework designed to enhance multi-step reasoning, and we now integrate principle from Q-learning in A-star. For example, using here the Q-value models to estimate the future rewards of our action taken to guide the decision making by the LLM. Plus, Q-star frames now this multi-step reasoning as a pure Markov decision process, where the states of the system represent sequences of reasoning steps and actions are the next step to take. So, maybe the most important sentence here, one of two, is Q-star, the new Q-star, uses here our known Q-value model to estimate the expected future rewards for specific state-action pairs. So this is very similar to the Q-learning that you know from reinforcement learning, where the Q-value represents the expected cumulative reward of taking a certain action starting from a given state and going on until you converge. So really, this is an important sentence. And this Q-value model helps the LLM to evaluate and select the most promising next step during the reasoning process. Now, if you are green grasshoppers, you say, hey, can we have a little bit more explicitly explained, so a different view? Well, of course. In general, the researcher divide between a system 1 and a system 2 system. So what is a system 1 mode, as they call it? So what is the problem? The researcher tells us even as the most advanced LLMs still face, and this is here June 2024, significant challenges and are prone to introduce errors, hallucination, and inconsistent statement as the number of reasoning steps grows due to their architecture of an autoregressive model. And they say now, okay, so in our LLMs that belong to the system 1 group, what do we do to fight against this? Now, we can construct sophisticated prompts, you know this is prompt engineering, DSPy, with extensive expertise to trigger here, yes, you know this. Or, since we cannot continue to pre-train GPT-4 system, maybe we can fine-tune then the LLMs with some massive task-specific corpus at the price of significant computational burdens. Or, the last step is here the alignment phase of an LLM. We can train here specific rewards models to rank here the candidate responses. So these are the old classical ways how you can improve here the, let's say, reasoning performance of a system 1 mode. So, more straightforward, you have here an instinctive decision-making process as a system 1 thinking mode, which are fast, but prone to errors and inconsistencies. And yes, you guessed it, we have a system 2 mode of operation. And this mode now solves complex reasoning problems, but it requires a more in-depth, a more deliberative and logical thinking steps, therefore system 2 mode. And you know the systems here. We have, for example, classical basic tree search algorithm, we have the Monte Carlo tree search, and we have A-star. Hello A-star, here you are. So, talking about deliberative, I had to check up what does it mean here, deliberation here in the context of AI, and I learned, hey, deliberation involves here an in-depth, logical and systematic evaluation of possible reasoning step to select the most promising one. It is akin to system 2 thinking, which is slow, analytical, and methodological, but it aimed at reducing the errors and improve here the performance of the accuracy of the reasoning process of our LLM in the system 2 mode. So this is now what we are focusing on for the rest of the video, and we start with A-star. You know that talking about reasoning, I introduced you here to this planning already in my last video. So let's have here the old ideas of enhancing here our LLMs with the planning. And as I've shown you in my last video, we have the 3 of sorts methodology to improve the LLM's reasoning capability by exploring here the intermediate steps toward the problem solving with a basic tree search algorithm. Now, in the same way, A-search here and the Monte Carlo simulations are applied to serve here also as a planning technique to enhance the performance of our LLMs, especially for complex reasoning problems. But unfortunately, the utility function that we use in these methods is either constructed from the LLM feedback. And you know the LLM are prone to errors, so this can be highly inaccurate in especially most complex problems, or it is so specific to each individual task that we simply have a computational threshold that we can't afford to do this for each individual task. And you as a green grasshopper may say, hey, so we need something like DSPy to a programmable prompt engineering approach. But now we take this amalgam and we move it over to the level of multi-step reasoning. And I would say, yes, beautiful, you got it to the point. So the authors of this new study, I'm going to show you in a second, say, hey, our Q-star methodology solely relies on training a Q-value model to guide our LLMs, and we will have a look at open source LLMs, to select the most promising next reasoning step in a multi-step reasoning process. And this pipeline can be easily applied to various reasoning tasks without modification, meaning without fine-tuning the LLM. And this is beautiful. So let me introduce you here to this beautiful study, June 24, 2024, Q-Star by Skyrock AI and Nanyang Technology University, improving here our multi-step reasoning for LLMs, but it works beautifully for vision language models with a deliberative, now I know what this word means, planning. And here you have it all that we just tried to summarize up until this moment. Now, unfortunately, I have to tell you, I read the study and I looked at this first figure that explains here the overview of Q-star, and I was not able to understand this. I saw here this paths to the terminal state and I was missing some X and Y. I was not sure in what mathematical space we are operating, so I did not get it from this figure. So you know what happens? I am becoming now a green grasshopper myself, and I have to start simple. So I looked back in the literature and I found here in May 2023 from OpenAI, they looked here at this complex multi-step reasoning process already at this time, and then let's verify step by step. And they reference in their work to an even older work here by Sato in 2022, who described here two distinct methodologies for training the reward models. And it was an outcome supervision and a process supervision. And for the rest of this talk, I'm going to focus here on the process supervised reward model, on the PRMs and how we can train them. You have here this beautiful publication by DeepMind here, Sato, November of 2022. And in this beautiful figure, you see here, you start with your base LLMs, you have a few shot prompting, you have your solution samples, you define your reward model, you do the re-ranking with the reward model, and you got your final answer with a particular error interval. And you see here all the interaction that could theoretically take place. Beautiful. But since I'm not a green grasshopper, I want to have it even more simpler. And Stanford had here this link to this beautiful homepage here, redblobgames.com, and they have an introduction to the A-star algorithm that I really enjoy, and I want to show you this. So they go now here, there are a lot of algorithms that run on graph, and they say, first we have the breadth first search. Explore equal in all direction, incredibly useful for game theory, not only for regular pathfinding, but also for some map generation to flow field pathfinding, distant maps, and so on. And then they're saying the second model is our Dijkstra algorithm, or as they called it here in the classical form, a uniform cost search function that let us prioritize which path to explore. So instead of exploring all possible paths equally, now it favors lower cost path. And we can assign lower cost if you want to encourage moving here on particular roads, and you can have higher cost associated to particular paths. If you have to climb a mountain or you have to cross a swamp, you get the idea. And then they have here A-star. This is now a beautiful modification of Dijkstra that is optimized now for a single destination. And let me follow their visualization. Here you see the breadth first search as it searches here the complete space. Now, Dijkstra on the left-hand side also does this, but a different methodology. But they also showed that here with the greedy best first search, if you know your target, look how fast this is. Done. And Dijkstra is still running. But both has pro and cons. Let's say you have, you block something out. So you see, Dijkstra analyzed everything and then came up with the shortest path, while the greedy best first search got the direction, notice halfway, hey, wait a minute, there is here a brick wall, I have to go around because there's no direct connection, and then this is not the shortest path, so Dijkstra wins in this respect. Also, greedy best first is faster. Now, let's say you're in a game, and in the middle, between your starting point and your end point, you have a swamp or a hill. You see here? So, with this model, you just go straight. But in the Dijkstra algorithm, it calculates also the cost, what it means, let's say in energy, to climb up here this mountain. So there's a lot, if you would go in a straight line, you have to use a lot of energy. You have very high cost, and you just can go around the mountain. So it's a little bit a longer path, but if you go for a cost-evaluated pathway, you see this is the best solution, maybe even the fastest solution. So this is a very simple visualization, but I think it gets you the core of the idea. And yeah, here you have Dijkstra, greedy best first, and A-star search. So Dijkstra works well to find the shortest path, but it wastes time exploring in directions that aren't promising. And greedy best first search explores in promising direction, but it may not find the shortest path. And A-star now uses both the actual distance from the start and the estimated distance to the goal. And this is the beauty that we will also find in Q-star. So it takes the idea of A-star, and this is the idea of A-star, and it transforms it on a much more complex level for Q-star. So I wanted to show you this for a simple visualization, and I don't have to tell you or show you 10 pages of mathematics for this. So A-star finds the right answer, like the Dijkstra algorithm, but it still explores much less of the grid functionality than the Dijkstra algorithm does, and you can see this simply here. If I extend here the wall to block it out here, but I open here something in the wall so that we are in the direction to our goal, you see A-star just calculates here the possible paths and does not calculate here, for example, this grid sequence. However, Dijkstra does calculate everything, so it takes more time, more compute. It is a more complex operation, and this is why A-star in this simple explanation is so beautiful. So, now to be a little bit more professional, how does A-star, the algorithm, works? It's an informed search algorithm that uses both the actual cost to reach a node and a heuristic estimate of the cost to reach the goal from that node. So we have two lists, an open list node that can be evaluated and a closed list of nodes that have already been evaluated. You start, you have a simple evaluation while the open list is not empty. You select the node with the lowest total cost from the open list. You move this node to the closed list, and for each neighboring node you calculate the cost. And if a node is not in the open or closed list, you add it to the open list, and if it's in the open list with a higher cost, you update the cost and the parents. So you have a beautiful, simple way to calculate, if you want here, the shortest path given the cost of this particular path or the energy of this particular path. So what you have, a very simple equation, you have the total estimated cost of the cheapest, less cost paid solution through the current node. So your function f of n is simply here g of n plus h of n, where g of n is the cost to reach the current node from the start node, hey, wait a second, and h of n is the heuristic estimate of the cost from the current node to the goal node. So you have here this equilibrium, what you already achieved, and you look forward to your end node that you want to know, okay, I can now calculate here a projection. What will be the cost if I choose different paths forward? There's a simple code explanation here in Python, of course, if you want to understand here the core logic and if you want to program this. But now, this idea of A star is now beautiful because we use it now to apply it now for the reasoning pathway. And imagine the reasoning pathway of multiple step reasoning is something similar like going through a graph of complex explanation and finding the most simple, the most shortest, the most cost-effective way for a multi-step reasoning. Beautiful. So you remember Q-star? Framework, design, improve multi-step reasoning. Unlike traditional reinforcement learning methods, here we use here with Q-star a plug-and-play Q-value model to guide the decision-making process of LLMs. Another most important sentence here is, now Q-star treats the reasoning process as a heuristic search problem. It sounds strange at the very beginning, but it makes sense because you are here, if you're looking here you search here for the optimal solution and you use a specific heuristic to apply this, and your search problem where each state action pair is evaluated based on its quality value, and this now estimates the future reward for the system. This is the core of Q-star. Q-star treats the reasoning process as a heuristic search problem where each state action pair is evaluated based on its Q value, which estimates the future rewards. So again, short summary, the key features of Q-star. We have a heuristic function. In the case of Q-star, our heuristic function is a Q value model as a heuristic. Then we have the whole process as a Markov decision process. It formalizes here the multi-step reasoning as this Markov process where states are sequences of reasoning steps and actions are the next steps to be taken. And we do have a Q value estimation of optimal values, 1, 2, 3. Now, to improve the reasoning without extensive fine-tuning or domain-specific adjustment, we have now to focus on the Q value model if you want to use this in our Q-star. You know, Q learning, our old friend here, is a model-free reinforcement learning algorithm that aims to learn here the value of an action in a particular state. This value, known as the Q, the quality value, represents the expected cumulative reward an AI agent can obtain starting from that stage and taking that action. And this Q value for a state action pair is calculated and updated using here a specific equation, the Bellman equation. Beautiful. Now, this iterative process in Q learning helps the AI agent to learn how the optimal policy, a new word, policy, for maximizing the cumulative rewards in a given environment, since the Bellman equation balances immediate rewards and estimated future rewards to iteratively improve the policy and guiding the agent to make better decisions over time. If you want to learn more about the offline reinforcement learning, I would recommend you start with this paper from UC Berkeley and Google Research from November 2020, my goodness. And here they explain beautifully here offline reinforcement learning. And to show you that Q learning is so important even in the latest research today, for example here an IEEE transaction on vehicular technology from June 14, 2024, they show you here for a mix of Q learning for a lane changing system, a collaborative decision-making method in multi-agent deep reinforcement learning. So this means you have your autonomous vehicle, you're driving here, and all the logic and the new research for your autonomous driving intelligence can also be based on here a mixed Q learning. So if you know Q learning, it can be important and it is still used today. Beautiful. This was Q-learning. Now, we encountered the term heuristic, and I think I did not get it what it really means. So, a specific chapter now on heuristic. A heuristic is a problem-solving approach that employs some practical methods or shortcuts to produce solutions that are not guaranteed to be optimal or perfect, but are sufficient for reaching an immediate goal. Now, in the context here of AI and computer science and everything, heuristics are simple strategies. Strategies used to make the process of finding solution more effective. Now, in our Q-star framework, a heuristic function is used to estimate the potential value of future action during the reasoning process of our LLMs. So, this heuristic function guides now the model in selecting the most promising next step in a sequence of reasoning steps, thereby improving the accuracy and the efficiency of solving here our complex problems. Now, in A star, what was the heuristic function? You remember this simple equation? So in A star, the heuristic function estimates the cost from a given node n to the goal node, to the final node. And we had here this simple function f of n equals g of n plus h of n. And h of n was the heuristic estimate of the cost going from the node where we are currently sitting on to the final node that we want to reach, our goal. Now, the algorithm in A star maintains here two sets. As I told you, an open set of nodes to be evaluated and a closed set of nodes that has already been evaluated. And the heuristic function helps now to prioritize nodes in the open set, selecting the node with the lowest function f of n value for expansion. And this ensures that the search process is both efficient and directed towards the goal. Now, the heuristic function in the Q-star method, please let me be absolutely clear about this, is now designed to balance two key components: our aggregated utility and our heuristic value. So let's start with the aggregated utility. This represents the accumulated utility from the initial state to the current state. So we had a start state, and after some steps, we are now at a specific state. We are sitting now on a specific node. And the accumulated utility from start to today's node is what we call an aggregated utility function. Now, the heuristic value function, h, is now the estimated utility of reaching the correct answer from our current node that we are sitting on, derived now, and how we do this foresight, if you want, derived from the optimal Q-value model. And you see, the heuristic function in the Q-star methodology is really similar to what I showed you before. Our f function now, depending on the state at a specific time t, or st for state, I have seen both forms, is simply g of state plus lambda h of state, where g of state is the aggregated utility from the initial state to the current state, and h of the state is the heuristic value represented by the maximum, careful, the maximum Q value of the possible next action. So the best next action as evaluated by our Q value model. And our lambda, this is a play factor. This is now a coefficient that balances here the importance between the dominance of G or the dominance of H. Great. So, aggregated utility. What is it? Now we come back here, calculated based on the process-based reward function that encodes here prior knowledge or preferences about the reasoning task, and then the aggregated function, ag, can be used in several types. You can have a minimum, a maximum, a summation, whatever you like. You have to experience this yourself for your particular task. So, for example, in the context of mathematical reasoning task, G, our aggregated utility, could aggregate intermediate rewards based on the, let's say, the correctness of the reasoning step as evaluated by the LLM, or the LLM gives out confidence scores, and you say, I only want to go with the highest confidence scores as evaluated by the LLM, or you have other task-specific metrics now that you want to integrate here. Now, the second function was the heuristic value function H, and this is simply derived from the Q-value model, as I've shown you now multiple times, which estimates the expected future reward of taking here a particular action. And this is, of course, done by using the Q-value of the best next actions among, let's say, the top 20 candidates, which can be represented simple that the function H of a particular state is now the maximum given we have an action A that is element of the top K set, the top 20 possible action, depending now on a policy that is parameterized with theta on a given state, S of t. The Q-value model, Q star, of a state and an action is trained to approximate here the optimal Q-value, indicating the expected reward of taking an action A from a particular state S or St at the time t. So for my green grasshoppers, if you want to be absolutely clear what this notation means, P denotes here the policy, which is just the strategy or set of rules that the model follows to decide on the next action. The parameter of the policy is normally designed with theta. In machine learning, these are the values that the model learns during the training to make accurate prediction or do some active decision making. And the parenthesis here, this notation means simply given the current state S at a particular time step t. So this current state includes now all the information the model has up to this point in the reasoning process sitting at a particular state S. The policy is more or less nothing else than the AI strategy to evaluate the moves. And the policy uses here the game's rules, the learned pattern, and the past experiences to assign now new probability to each possible future move. So, just to be clear, I was asked, hey, who makes or what system makes now the decisions? And I want to be absolutely crystal clear. Your LLM, with all its restriction, with all its incapabilities, with all its not the top-notch quality of its pre-training dataset, the LLM ultimately makes the decision. And this LLM relies here on the chosen policy to evaluate and rank the possible actions, ensuring that its choices are informed by the past learning and the current context. So the policy, if you think about it, the policy P with the parameter thetas that are given provides here a structured framework for the LLM to evaluate and decide on the next step in a reasoning process. So you say, hey, great. So we have now in Q star, we have our LLM, we have now our Q value model, and we have the policy depending now on the parameters theta. Beautiful. So let me explain now in the next chapter the policy pi here, or P, as I call it in German, in the Q-star method. So what do we have? We have an action selection. We have our top K, top 20 action candidates. We can calculate here the heuristic value function H of a particular state S at the time t. And this is guiding here the search process. I leave this here for my little grasshoppers to read carefully if you want. But let's do an example. Let's say a self-driving car needs to navigate through the city streets, making decision at each intersection, when to stop, let's say for a pedestrian, how to handle different traffic signals, and much more. So again, in this context, and what I want to show you here, the policy is a set of rules that you define, or you let a machine learning algorithm to define, that a self-driving car uses to decide on the action based on the current state of its environment. So let's start here. what are the states that we encounter here in this particular example? A state can include various pieces of information about the car's environment, such as the location of the car, the status of the traffic light, the presence or non-presence of pedestrians, how far they are away, of nearby vehicles, moving vehicles, stationary vehicles, emergency vehicles, and the speed of the car, and the list goes on. Now, what are the actions that you can take for your particular example? The car can move forward, turn left, turn right, stop, accelerate, deaccelerate. That's it. It cannot just jump in the air and fly away. So you have action defined, you have state defined, and now the game starts. Now, for the LLM to have guidance, you define a rule-based policy. This is the simplest form of a policy, and the rule-based policy is simple. The rule: if you are at a red light or in front of a red light, you stop the car. Or if at a green light and no pedestrians are crossing, hopefully, you can move as a car forward if the path is clear. Or green light and pedestrian are crossing, please be so kind, stop and wait for the pedestrians, for the human to cross. And you get the idea. And then you write down all the rule-based policy, and there you have it. Or, as I've showed you much nicer, and what we will use here in the Q-star methodology, a policy can also be derived from machine learning, particularly from reinforcement learning. What a coincidence, where the car learns the best action to take through trial and error and feedback from the humans and from the environment. For example, the feedback a pedestrian will give you if you run over them. So here we go. So we have the reinforcement learning policy example. We have a state representation, we have a selection of action we can do. So we encode a state now as a vector of features, including here all the different features in a multidimensional vector space, the traffic light status, the presence of pedestrian, the car speed, and so on. You know this. This is our typical vector representation. And then action selection, we use a trained model, any neural network will do, that takes the current state as an input and outputs now a probability distribution over possible next actions. But please note we have a probability distribution, maybe a beautiful Gauss curve. And then you select the action with the highest probability or a sample from this distribution, depending on the task. Now that you have here the policy, you have the training of the policy. So the self-driving car now collects data by interacting with its environment, making decisions based on the rule-based or on the reinforcement learning, and observe the outcomes, which will kind of be the reward function. So it receives now reward from its environment, from its sensor, based on its action. Positive rewards for driving safely and negative rewards for unsafe actions. And over time, the car adjusts its policy to maximize the cumulative reward, learning to make better decisions here in all the different states it can be in. Beautiful. Now, simple example for the learned behavior. Car is in intersection with a green light, no pedestrians are inside, and there are cars stopped at the red light in the cross street. Now, normally you would think that the policy action that the AI decides to take next is green light, everything is free, the car decides to move forward through the intersection. Beautiful. However, let's say we are at the intersection with a yellow light and the cross street light will turn green soon. Now, this is a very nice car and it learned here the policy action. Hey, if it's yellow, it's better that I as a car decide to de-accelerate and prepare myself to stop in front of the traffic light. You see, such an easy way. If here you want to see the complete optimization process in Q-star, like I just showed you here in my last 5 minutes, 10 minutes, here you have it again for my green grasshoppers, generating here the possible action, selecting here the top 20 actions, evaluate the actions using now the Q values, compute the heuristic value function. This is guiding here your reasoning process, and then you have an iterative optimization. Beautiful. Now that we know all of this about the simple A-star, we know that we now can include here the Q learning function models here in our Q-star model. as if you want here as a heuristic of the system. Now let's look at the performance of Q star. How good is it? And we go here to original study, and these are the results. So, comparison of Q star on a particular benchmark dataset. And we have here GPT 3.5, GPT Turbo, GPT-4, beautiful. So what we have classical, the base model, the pre-trained model, then we have the supervised fine-tuning, and then we have an alignment, either with a reinforcement from human feedback or a DPO or PPO, whatever you have here is a PPO, and you have an accuracy on this particular dataset. And as you can see here, ChatGPT Turbo with a zero shot reaches here an accuracy of 77%. Beautiful. And now the authors of this study say, now we take here a very tiny, a very old Llama 2. And the tiniest model is a 7B zero-shot model. And we have a look at this. And if we do no alignment, no classical PPO or DPO alignment, but we do a fine-tuning on a particular mathematical set, and then in the verification, we choose now the best of n methodologies. And here we have here a process reward model. We achieve 72%. If we go for the best of n with now the quality, the Q value model, we achieve 74%. If we now go with the Q star model, and we use here the quality value model only, we reach 78.8. And if we add here this reward model here, we reach more than 80%. So they wanted to show you here the result, and this is a very particular format chosen by the authors of the study to show us, hey, even with a very old Llama 2 system, a very tiny system, in the logical reasoning task with, let's say, 80%, we come close to a beautiful, huge ChatGPT Turbo zero-shot performance. So interesting, but this is just one dimension here of the evaluation, no? Let's look here at the mathematical data set. How does here this same system behavior happen? And now we do not have only an old Llama 2 7B, but now we have, careful, the DeepSeek version 1. You know there's now version 2 out at the moment recording this video on the mathematics on also a 7 billion free trainable parameter large language model. Beautiful. So we don't know here the supervised fine-tuning here for the DeepSeek version 1. Beautiful, but we know the alignment happened also with a PPO. And for the Llama here in this particular way, we also had a PPO. But for these two Llamas, we do now the best of an N in a Q value model, and we reach 46.8. And in the Q star model, we reach 49.1. Okay, so from the Llama 2 7B, however, they have been treated. Q star for this particular Llama 2 reaches here the highest accuracy in the tested variation of Llama 2 7B. For DeepSeek, we have here also the best of N. This is just the Q value model, so not the Q star. We have 54.3. And if you do now the Q star, so whatever I told you now in this video, Q star based here on the heuristic of a Q value model, we reach now 55.4%. Now in my little mind, I thought, okay, so in the classical known way of Q value models and the best of N trials, I reach 54.3%. And now doing all this real, not easy to understand Markov Decision Policy Optimization Q value model plus reward model that is based on a process optimization and then on the complete Q star optimization methodology. And I reach now 1.1 percentage point more performance. I guess you have to choose for your part, for your system, is this worth it? Or is this just an artifact for this particular model of DeepSeek version 1? Because if you look at the Llama 2, and unfortunately there's no Llama 3 that was done by the authors of this study, at least you have here from 46.8 to 49.1. So here you could argue the jump is a little bit bigger than just 1 percentage point. Okay, but what they wanted to show you, and as they have here in the marketing material, this now beats here a Gemini Ultra, which reaches here only 53.2%, and this here reaches 55%. So this methodology outperformed here Gemini Ultra, which is correct given a specific data set and understanding here all the complications and limitation of the system, but it is really up to you if you want to go this way. So just be careful, look at the beautiful published results, but do not just go with the, let's say, with the marketing that it outperforms here the best Gemini Ultra or whatever. Just have a look. They have here absolutely precisely, beautifully stated their results. Have a look at the results yourself. And here you have it. Now this is the final piece, as the authors of this study say. What did we achieve? Let's have a look at this. So they say, hey, in the latest, best and brightest and most complex model, we formalized the multi-step reasoning of LLM as a Markov decision process, where the state is a concatenation of input prompt and the reasoning step generated so far. You remember we are sitting on a particular node in our graph, and the action is the next reasoning step, and the reward measures how well the task is solved, all by the LLM. So you have to have an LLM with a high complexity, with a high understanding of the methodology, and with a high quality pre-trained data set. Otherwise, the LLM will simply fail on this point. And the authors go on and said, hey, we present several general approaches to estimate now the optimal Q value of state action pairs. And this means here the offline reinforcement learning, showed you the publication, the best sequence from the rollouts and completion with strong LLMs. So it is noteworthy that our methods only need the ground truth of training problems and can be easily applied to various reasoning tasks without modification. Yes, it is true, you do not have to have an SFT, supervised fine-tuning, but I think the methodology itself, if you encounter it for the first time, it is not that trivial. And then the authors go on, we cast solving multi-step reasoning task as a heuristic search problem, where the objective is to find the most proper reasoning trace with the maximum utility function building upon A star. Our deliberation framework Q star leverages now the Q value model as the new heuristic function, and this heuristic function guides now the LLM to select the most promising next reasoning step in best first fashion. So you see, I've shown you all of this here in a very simple visualization from a game company, but I hope here that I've shown you the main idea, because you can write here a lot of complex formulation, but I wanted that you get the idea in the easiest possible way, in the most beautiful path here that we cross here the complexity of our graph explanation task. Beautiful. Yes, you can find here all the code. It is available for you if you want to try this. So this is just for me. Never mind, you can read it or not. I wrote down what are now the components here of the Q star method. At first, we have our LLM, which decides everything. This is the primary model that processes here the query, generates the potential reasoning step. It is hopefully capable of understanding everything and generating a human-like text based on the input it receives. Then we have our Q value model that we know. And this Q value model estimates, careful, it estimates the expected future rewards for specific state action pairs. So it helps the LLM to evaluate the potential success of different complex multi-step reasonings by predicting the cumulative reward of taking a particular action in a given state using Bellman equation. And then we have the policy, the learned policy. And this now represents the strategy the LLM uses to choose the next action based on its current state, based on the node that is currently sitting. Policy is parameterized by data, which are parameters learned during the training, and this policy determines the probability distribution of possible next action. So there's a lot of learning. You have all the pre-training of the LLM, you have all the policy ideas that fit to your task. You have this policy must be learned here. This is not a simple task. Then you have here the Q value model that estimates the expected future rewards. This is not a simple task. So just be aware that you are operating here in a real, for me, complex environment of potential foresights, of potential future functional values, but all based on the, let's call it, limited artificial intelligence of an LLM. Now, those are the steps. I also like to have here step 1 to step 6. What is the process? Show me here the process as it unfolds over time. Simple example here in a mathematical thing. Here I have here solve the equation 2x plus 3 equals 7. So policy generate actions. The LLM now says, hey, might be subtract 3 from both sides, or another action might be divide by 2. Now the Q value model evaluates those actions based on what it learned, based on what it knows already, and based on here future, let's say, projection. And here the Q value model estimates the future reward of each action, getting here the best and perfect solution. And the heuristic function guides now the selection here of the action, and it's combining the past rewards and the future prediction. And then the LLM, in its beautiful glory of artificial intelligence, selects now one action, and this one action is from this 2 action, subtract 3 from both sides as the next step that should lead to the immediate result. And then you have to update and repeat. It is an iterative process. So then our mathematical equation reads now 2x equals 4. And the process repeats until the equation is solved. And since we already have here in the policy generated action divide by 2, so you have an idea that we will come here to a real solution to our mathematical equation. So you see, such an easy topic, but you can run here in the simple way through it to understand what element of Q star is doing what and how it is combined, where are the probability distribution that you have to be careful of, that you have to pre-train your LLM on, how you decide your policy. This is not an easy task, and we have not even talked about the numerical implementation of this code and which boundary condition you should choose for not just to go crazy. I have here another kind of information about the correlation between the policy and the reward model in Q star. So I just wrote down for me, what is the policy, what is the role, the definition of the reward model. The reward model is used to update the Q values, which represent the expected future rewards of the state action pairs. It provides feedback to the policy on the quality of its action, therefore the Q value model. Then I have here the correlation between the policy and the reward model. Yeah, this is just for me, no problem. And then here a summary of the causation steps in Q star. I like to have this ready for me, because if I come back in a year and I don't know, multiple years, if I still have here AI, I just want to understand it on a single piece of information. So the policy generates the actions, the reward model provides the feedback, the Q values guides here the future action, and over time the policy improves here better strategy, selecting better action that more likely result in higher rewards and therefore in a better overall solution set. Beautiful. This is it here for Q star. So I hope you are now familiar with the latest, with the most complex, with the most interesting solution to come up to help our LLMs in a multi-step complex reasoning pattern. And I think for the moment it can't get any more complicated or compute intensive like Q star. If you found another model, please leave me a comment here in this video, because I would be really interested to see where our path to optimize the multi-step reasoning capability of LLMs, where this will lead us. I hope you enjoyed this video. Maybe you learned something new, maybe you found it interesting, and it would be great to see you in my next video.